Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're moving on from carboxylic acids, and we're going to begin looking at the derivatives of carboxylic acids. If you recall, we defined derivatives of carboxylic acids as molecules that yield carboxylic acid upon the reaction of water. Such molecules were given in the preparation of carboxylic acid section, and we want to review those now. The first ones that we're going to look are the acid halides. Acid halides. Now, acid halides can have various structures, such as this molecule. Its IUPAC name is ethanoyl chloride. Two words. And its common name is acetyl chloride. Now we'll look more closely at the derivation of these names. Consider the nomenclature at this point as just examples. If you look at it closely, however, you can easily see that they're named after the carboxylic acid, where the ic acid ending is dropped and replaced by YL chloride. But acid halides are not found as chlorides only. For example, you could have an acid halide that is a bromide. This is based on benzoic acid, and hence, drop the X acid, you'd have benzoyl bromide. Two words. Now benzoyl bromide, because benzoic acid is a common name that was adopted by IUPAC, it's both the common and IUPAC names, benzoyl bromide. Both these molecules are examples of acid halides. In the case of the acid bromide, bromine is a weaker base than chloride and hence a better leaving group. Because of this, acid bromides are more reactive, typically so reactive that if they're prepared, they're used immediately upon reaction. Acid chlorides, on the other hand, can be stored more readily. And as a result, when we refer to acid halides, more often than not, we're referring to acid chlorides. These molecules react with water to make carboxylic acid. And you can review your preparation of carboxylic acid section to confirm that. The next functional group we want to look at are the acid anhydrides. Now the acid anhydrides consists of two carboxylic acids that have lost water that are linked together. For example, this molecule is carboxylic acid attached to another carboxylic acid where you've lost water. Based on ethanoic acid, this is ethanoic anhydride. Likewise, common name, acetic anhydride. And of course I didn't have room for the E there. Acetic anhydride. Anhydrides can be symmetrical or asymmetrical. Here we have propanoic benzoic. Okay. So we could call this by IUPAC benzoic space propanoic anhydride benzoic propanoic anhydride, or the common name would be benzoic propionic anhydride. Okay. All right. The next derivative of carboxylic acid functional group that we want to examine is the ester. We've run across esters throughout the course in alcohol sections. They're carboxylic acids where the H has been replaced with a carbon. Such as found in this methyl ethanoate, 2 words. Ethanoic acid, the ic acid is dropped and 8 is added, and the alkyl attached to oxygen is a separate word up front, or the common name methyl acetate. Amides have some nitrogen, which may or may not be substituted, just like carbon. And you may have, for example, a CH3 here. This whole unit, if replaced with an OH, would be a benzoic acid. The oic acid is replaced with the word amide, and so this becomes a benzamide. Of course, we have a methyl off the nitrogen, so we would say N-methyl benzamide. And because it's based on benzoic acid, it would be both the common and IUPAC names. The last functional group that is a carboxylic acid derivative is a unique functional group. It is the nitrile functional group. It is different from all other carboxylic acid derivatives because it does not have the C double bond O. Now, in some cases, the IUPAC nomenclature is taken by adding the word nitrile to the alkane root. The alkane is a 2-carbon chain in this case, so it's an ethane. So the IUPAC name is ethane nitrile. The common nomenclature involves taking the carboxylic acid name, such as acetic acid, dropping ic acid, and adding the term onitrile. So the common name is acetonitrile. If you did this with the benzoic acid derivative, the common name is the IUPAC name, and so we have benzonitrile. Okay, so there's some examples of functional groups with structures and names. What we want to do now is take a look at the general reactivity of the carboxylic acid derivatives as a group. And of course, what we're going to do is consider all of the carboxylic acid derivatives other than nitrile, because they all contain the acyl functional group. That is, every one of these carboxylic acid derivatives except nitrile consisted of this type of acyl group with a leaving group attached. Now, the ease with which the group leaves determines the relative reactivity. And if we examine the leaving groups that are possible, X minus halogen leaves or is a weaker base than the carboxylates. So X minus, actually let's move this over, X minus is a better leaving group and hence more reactive. So in leaving group ability, the carboxylate is less than the halide. The carboxylate is less a leaving group, right? The alkoxide, likewise, is a less, because it's a stronger base, is a weaker leaving group. So is less good as a leaving group. NH2 minus, again, we increase the basicity, again, is less capable of leaving. And then, of course, the least capable is the most basic. CH3 minus and H minus. If X is any of these, then it is the most basic and least likely to function as a leaving group. So in terms of leaving group ability, over here we have the poorest leaving groups. And over here we have the best leaving groups. Now, at some point, the leaving group ability must get so bad that there's a point at which the functional group will not leave. In fact, that demarcation occurs here. The CH3 and H minus are so bad they never leave. So when a nucleophile attacks molecules where X is CH3, the nucleophile accounts for nucleophilic. It's attacking the C double bond O, so it's attacking an acyl group, nucleophilic acyl. But because nothing leaves, it's called addition, nucleophilic acyl addition. All of the others, the carboxylic acid derivatives, they undergo a different mechanism. The nucleophile attacks, so it's nucleophilic. It attacks the carbonyl, so it's a nucleophilic acyl. But this time you kick out the X group, nucleophilic acyl. Because the nucleophile comes in and the X group leaves, it's substitution. So carboxylic acids differ from aldehydes and ketones in that they undergo nucleophilic acyl substitution, while aldehydes and ketones undergo nucleophilic acyl addition. We can show this quite nicely. In the case of aldehydes and ketones, you have R, C, double bond O, R prime. You have a nucleophile attack. It's attracted to delta plus on the carbon. The pi bond ruptures, and we get RCO minus, R prime, and a nucleophile, where R may equal and R prime equals H or alkyl. Now, this is what occurs for aldehydes and ketones. The mechanism is referred to as nucleophilic acyl addition. Now consider what happens with carboxylic acid derivatives. Carboxylic acid derivatives that have RC double bond OX react with a nucleophile, and in the first instance the attack is perfectly identical to what happened for the aldehyde. You get the RCO minus intermediate, but X is a weaker base, and as a result X is a good leaving group. So the pi lone pair of electrons reform the pi bond, and X is kicked out as X minus. And then you've reformed the C double bond O, you have the nucleophile there, and you have X minus. Good leaving group. So in the case of carboxylic acid derivatives, the reaction mechanism is identical for the first step, but it continues on, and so the mechanism is nucleophilic. Acyl substitution. And lastly, with the different carboxylic acid derivatives, note the better the leaving group, the weaker the base that X is, the faster the reaction. And there you have it. Carboxylic acid derivatives react differently than aldehydes and ketones, simply due to the leaving group of ability of the X group versus hydrogen or carbon. Well, next lecture we're going to take a look at the first group of first functional group in our list of carboxylic acid derivatives, the acid halides. We'll look at them in much more detail. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.